Hi my friends, we continue with finite element analysis, and today we'll study analysis static, load, pressure and subject both parts and assemblies. Let's try to understand and to learn how to use these interesting tools. We start with the pressure on parts. To do this, I have a model here. What we see here, we see an amphora. Yes, I assume this to be an amphora, like in Pompeii. We have to model this part, and then we'll apply pressure inside it, and we'll see a simulation of what happens with the amphora. Yes, let's start. New standard part. The dimensions are here. Start sketch. We start here by making a zoom out to see a dimension here. We look at the bottom. Yes, we have to find a point at about 200 on Y and 55 on X. Well, this is not so this is why we change a little the zoom by using the wheel of the mouse. Yes, and now this height is okay about, and this is also okay. That point is here about. We keep in our mind where it is, and we start with a line from here, and we literally draw the contour. Yes, by using methods you learned. I didn't find that point, but this is a good start. We have the contour 1, 2, 3 arcs, like here. 1, 2, 3 arcs. We continue by dimensioning the radius of that arcs. 100 here. 45 and also 45, and now we place, you see, this point on the axis. This point is on the axis of the amphora, so we have to project the Y axis as a center line, and we place coincident this point on this line, but another altitude. Let's see what happens. Very good. The altitude is 60 millimeters. 60, and the total height is 200. 200. Here is the diameter of 110. Now it's fully constrained. Now we add, as you can see here, an offset of 2 to the inside of this contour, and then we'll cut this horizontal, and here we don't need to make anything because there is an axis for that revolving final. Good. Let's apply offset to the inside of 2 millimeters, then a line at the top from here to here, and trim here, but oh, I forgot to change this setting. Now I changed it, and also this one is wrong as a line, but the assembly of dimensions and everything is very good. You have to work a little here, because there is an ability to place an arc after another. Now we apply revolve. Yes, the computer inventor in the computer knows everything, so revolve is just the preview, is the final. Okay, we choose the material, which is brass, B from brass, soft yellow. Oh, what nice! What nice body! Let's see what are its data. As usual, with eye properties, the material is brass. Update 2 kilos. Yes, 2 kilos is this part. Okay, let's apply the stress analysis. We don't use environments because we have here always we have the same icon of a tool. Create study, static analysis. Let's write here pressure, excuse me, analysis. Analysis. I have a new keyboard and this is why I make a lot of mistakes. Okay, the material we know is brass. Fixed is the plain bottom. Apply, and this is the constraint, and the pressure is applied automatic phase chain. We check this option, and we choose to place 0.1 MPa, megapascal, which means a bar. Yes, a bar is equivalent with 0.1 megapascal. You say, well, but the atmosphere has a bar. What you do here? I add inside this body supplementary pressure of another 1 bar, 1 atmosphere. You see, instead of 1 point or surface, all of them, because of this automatic phase check, have the same glyph, this group of vectors which appears on all faces. Okay. One, two, three. We don't have to do anything but to apply simulate. Run. Let's see what happens. Now we have a safety factor as a good suggestion about what happens with our object. You see, it's very nice. Animate. Okay. Wow. What a beautiful behavior. Good, but this is exaggerated. Yes, if we apply actual deformation, it is very reasonable. You see, nothing is happened. But we see here an extra red stress, and we want to know how much is. We apply maximum and minimum as well. Maximum is 4.4 megapascal. Megapascal is also for stress a measure, and minimum is here. But I told you the safety factor is more suggestive. Double click on it, and we have a maximum and the minimum in the same place. Look, it is not the same, be sure, but it's very interesting. Animate. There is a variation. Yes, but not so important. Good. What we find out from here? We find out that everything is okay, and the von Mises stress is not so great. 4.4. This means 0.4 kilogram force by square millimeter. Yes, this is not great. Let's change the thickness of our object. Let's make it smaller, 1.6 millimeters. Finish sketch. Stress analysis. Simulate. Run. We try to make as thin as we want. Maximum of stress is on the red zone, and minimum is on the bottom. yes, but it's still small, this stress. Good. What I see I don't like is that when apply animate, not actual but exaggerated, I see here something I don't like. Yes, this is why I think that we can increase only the thickness of the bottom. We can do this very simple by adding an extrude. I create a sketch, I project geometry, this geometry, finish, and I apply extrude of 3 millimeters, say, okay, and a rounding fillet of also 3 millimeters. Okay, stress analysis, simulate. Oh, I have to change the fix constraint because this is not the form of surface is disappeared, yes, delete, and I apply fix on the new bottom. Okay, you have to make a lot of changes to make an analysis and a simulation, of course. Good. If we look from the side and we animate, it seems to be an improvement here. Take your time to make other changes and to observe what happens. 5 years ago, I created this model of a hydrophore of 4 cubic meters capacity, and you can see some details. There are some level indicators here, a manometer, and you can see for yourself this by using this link. Okay, go to this link and see what it is about. All the description here, and you can download all the components and data of this interesting model. I made this for you here. This is the assembly with all components here of this hydrophore. As usual, you can download for yourself all these components together with the assembly by going to this link, tutorials, from fastgroup.ro, where you see me in the picture, and you go to tutorials, and here you download by clicking this zip. You unzip it and put it in a directory where you want to open. Good. Let's see how we can apply pressure inside this volume. Let's see a little how it looks. You see, this is all the assembly. We can go inside, as you know, by choosing the half section view. Yes, there are some options. Half section view is by default, and you choose a plane, for instance this one, and you can see everything here inside this object. Very interesting. Yes, we don't do this. We go to our interesting domain, stress analysis. Create study, static pressure on an assembly. Okay, and now we don't start by applying simulation, since we don't know which materials are here. Oh, there is steel, but not, and stainless steel, but not all over. There are some objects like the manometer. This is the manometer here, you see, which is not part of our study course. And other things, glass tube indicator. Glass tube indicator is for finding the level of a liquid inside this hydrophore. So we don't study this. Yes, the solution here is to open this and to select elements which are not part of the problem. For instance, manometer and glass tube indicators exclude from study. We don't want Inventor or finite element analysis module to deal with these small things. Good. And now we go directly to applying a fixed for this foods, the surface on the bottom, they are fixed. Okay. And to apply a pressure of also automatic. You see, this is an assembly, yes, not a part. 0.1. Another case of 1 bar, 0.1 megapascal. Which are the faces where I have to choose faces? I enlarge, I make zoom in here, and this is selected. I wait here and I select the interior face. You see a difference here? Yes, I select inside because I want to apply inside this pressure. It seems to be necessary to apply also on the other and the other. Select other. I wait. I still wait here, and I wait. Oh, this is considered, you see here, yes, because it's the same component, all this. It has two rounded faces, and they are all with force on them, with pressure on them. And now I wait here, and three of them, three glyphs must appear. 1, 2, 3. Yes. And now every face is implied in this study of pressure. You can see them here. Good. Okay. 1 bar, 0.1 megapascal. Since we selected assign, constraint and load, we can activate the simulation. There are some thin components, and they will be treated as solids. This one and this one. This is 700 millimeters, and this is 1,500 millimeters high. Yes, let's see what happens. They will be considered as solids. Okay. Waiting the run, I want to tell you that only the manometer was excluded from this simulation, and this makes a longer duration of this running. I'll tell you when it is finished. Okay. Okay, look at the result. The time for running was about 8 minutes, and we have some interesting elements. Look how this looks. Yes, we can see the vectors inside. I didn't apply any welding, yes, only constraining in the phase of creating the assembly were applied. Only constraints to be made, insert, and other constraints for assembling. This is why it looks like you see. Let's animate. This is very interesting. Yes, we can see how these components are changing during the simulation. Okay. And now I choose actual. Actual doesn't present such great deformation. We can see something here. If you are interested in this domain of studying pressure, stress, and other things for recipients, you can take your time and repeat what I did. Okay, this is all for today. Bye bye.